All right. This is the last slide we did on Wednesday. Dr. Davis has lost his special pen that works on his special tablet. Bum, bum, ba-dum. 12:2. Well, anyway, this reaction, this problem that we did on Wednesday is figuring out a rate law from given experimental data. We always want to pick an experiment where one of the reactants is constant and look at how change in the second reactant affects the rate. And so, I put 2 to the n equals 4 here, but what does that really mean? And so I wanted to just maybe be a little bit clearer about that. The factor of the concentration, so the change in concentration to the x power equals the change in rate. Okay. And so for NO, right, we look at this first experiment again, the concentration doubled, right? So it went up by a factor of 2 to the x, and then the initial rate quadrupled approximately. It's because they wanted to leave you with 2 sig figs, right? This is 1.25 times 10 to the negative 5th. You multiply that times 4, you get exactly 5. But they wanted just 2 sig figs, that rounds to 1.3. So the rate goes up by a factor of 4, and so 2 to the x equals 4, x is equal to 2, so it's second order. And so that's what we did on Wednesday. I just wanted to make sure we were super clear on that before we move on. Any questions or concerns with solving those kind of problems? Okay, hopefully you got some good practice in the ALEKS. If you do have any questions before the quest, holler them out now or shoot me an email during office hours. Okay, so first order reactions. Remember we talked about how the order of the overall reaction is equal to the order of the components all added together. And so let me back up just a second. We said that this reaction was second order for NO and first order for H2. So what's the reaction overall? Third order, yeah. So this is a third order reaction. Right. Now, third order reactions get a little tricky. They get trickier the higher the order is in terms of doing the math to calculate it. And so we're going to start with first order and move up from there. And so in a first order reaction, because there can only be one reactant, right, if it's first order, A is going to sum products. Remember, we don't really care how many products there are. It could be A splits apart into B plus C. It could be that A reacts to form B. It could be any number of things. And so we know that to write the rate in terms of A, the rate is just the change in the concentration of A over time. Now, A is a reactant, so what do I need in that equation?
Negative.
Yeah, we need to make it negative. Again, anytime we have, we're talking about the rates of a reactant, that rate sign is negative. Now we also know that the rate is equal to K times the concentration of A. Okay? Now these two look similar. They both have rate on the left-hand side. When we see this ratio of the change in concentration over time, we call this a rate expression. And when we have rate equals the rate constant times the concentration, we call this the rate law. Okay, so those equations, don't get them confused. If it has that rate constant K in there, it's the rate law. If it has that ratio of concentration change over change in time, that's the rate expression. Now those rates should be numerically identical, right? And so we can work with that. And so because those rates are identical, we can combine these two and say that negative delta concentration of A over time is equal to K times the concentration of A. Because those two rates are the same. Now, we can do a little algebraic rearrangement here. And when we do, we get these two equations. On the left, we have this exponential decay. In other words, if it's a first order reaction, we see that the concentration goes down exponentially based on that natural number E, right? Now, this is okay, and this is a nice curve, but as scientists, man, we really love the linear trends because those equations are easier to deal with. And so it turns out if you take the natural log of the concentration, well, the natural log of everything, but the natural log of concentration gets rid of this E here. And so now you'll notice that our y-axis has changed from concentration of A to natural log of the concentration of A. So a couple things to point out. The concentration of A, just in brackets like this, often has the little t down here. Down in the graph, it does. Here, it does not. But whether or not it has the t, when we just give the concentration of A, this is the concentration at any time. Okay. The concentration at any given time. Whereas A naught or A sub 0, right? This is the concentration at time 0, and time 0 is the beginning, and so we call that the initial concentration. And I'll just put in there T equals 0. And so if we look at this from a linear trend point of view, this is our y, and it's a little backwards, but this is our m, our x, and our b. And so y, natural log of A, is our y-axis. Time t is our x-axis. The slope here is negative k. And then that y-intercept is the concentration, the natural log of the concentration at time 0. So this is very useful for us when we want to calculate a given concentration, and we know the time and we know the rate constant. So let's do a quick example. Here we have this reaction, cyclopropane converting to propene. We know the rate constant that's given. It gives us a temperature. I mentioned on Wednesday that any rate, because it's dependent on the speed of the molecules and how often those molecules collide with one another, any rate is going to be very temperature dependent. We'll take a better look at that on Monday. But anytime you report a rate constant, you see a rate constant, it should always have a temperature associated with it. And so if the initial concentration, well, that must be, I'm just going to put Cp for cyclopropane. Cp naught is 0.25 molar. What's the concentration after 8.8 minutes? Well, we know our equation from the previous slide. the concentration of Cp is natural log concentration of Cp is equal to the natural log of Cp naught minus Kt. Well, we know Cp naught, we know K, we know T. We can do this, right? So the natural log of the concentration is equal to the natural log of the initial concentration, 0.25, minus K, 6.7 times 10 to the negative 4 seconds per second, and our time. Now our time is 8.8 minutes, and our rate constant is in inverse seconds, and so we have to do a little bit of conversion here. And so 8.8 minutes times 60 seconds, I'm just going to go ahead and put this here, 528 seconds. Okay? Do a little math and figure out the concentration of Cp after 8.8 minutes. How do we get rid of natural log?
Sorry.
Okay. How do we get rid of natural log? Yeah, e raised to whatever number we're interested in. Okay? And so the concentration of Cp is equal to e raised to the negative 1.74, which is 0.18, I suppose it should be, since they're only given 2 sig figs. 0.18 molar. Okay. Didn't quite leave myself enough room for that example, but that's the idea. So now, similar question, we're just solving for something else. How long is it going to take for the concentration to decrease from 0.25 to 0.15? Well, natural log 0.15 equals natural log 0.25 minus 6.7 times 10 to the negative 4 per second times t. Now notice that it wants this in minutes, so we'll have to do a little bit of conversion when we're done.
Dr. Davis,
Yes.
where did you get the 528 seconds to begin with?
So
Oh, it's 8.8. I'm sorry.
8.8 minutes. Yep. Has to be 528 seconds.
Cool.
And it has
Thank
to be
you.
in seconds because that's the unit on our rate.
Cool. Got it. Thank you.
So for part B, who's got an answer? Well, first, let's just make sure we're in the right ballpark, right? 8.8 minutes took us down to 0.18, right? We're going all the way down to 0.15, and so it should take a little bit longer than 8.8 minutes. Hopefully your time is longer than that. What'd you get for your time for this one?
Is it like around 12.7 minutes?
I'm good with that. I'm gonna put 13 because it's just 2 sig figs, but yeah, it's about 760 seconds, which gives us just under 13 minutes. Excellent. Okay. All right, this last one. How long does it take to convert 74% of the starting material? And our starting material is this cyclopropane. We want to convert 74%. Now, there's a couple of ways to answer this question or to work through this problem. In this particular problem, they gave us the initial concentration of 0.25 molar. But we could answer part C even if we didn't know the initial concentration. Right? Because in terms of a percentage, the initial concentration is, well, 100%. And so I'm going to write it that way. I'm going to write the natural log, we're going to come back to that. The natural log of the initial concentration, well, that's 100%, which is 1. And if 74% has been converted, how much is left?
26.
Yeah, 26%. So 26%, 0.26. All right, so this is one way to do it. Again, you could take the molarity, plug in 0.25 molar here, and take, okay, 0.26 times 0.25, plug in 0.065 there. You'll get exactly the same number, right? And to me, it's easier to just think about it in terms of percentages. So we start with 100% always, right? And we end up with 26% because we've converted 74. Minus, we know our K, so -4 seconds. And we're solving again for time. And so in part B, we got rid of just 40%. And now we're going to get rid of 74%. And so it should take even longer. So what time do we end up with to let 74% of the material react? Don't forget to convert it to minutes.
Dr. Davis, is
Yes.
there any possible way you can show the algebra to solve this equation?
Sure. So you're going to take the natural log in your calculator first, right? So 0.26 natural log is -1.35 equals natural log of 1 is 0. I should have known that off the top of my head. And 0 minus something is just negative something. 6.7 times 10 to the -4 per second times t divided by 6.7 times 10 to the -4 divided by, well, my buttons are in the way, but you divide by the same thing.
Thank you.
Yeah. And you get t, and hopefully your time is like something like 2,000 seconds. And that 2,000 seconds becomes 33 minutes. Okay, so that's using the what we call the integrated rate law for first order reactions. In the next Alex assignment for next week, there's a good bit of practice with that because we use it a lot. Okay. All right. So if we are just given a graph, in other words, if we just have some data, we don't really know anything else, But we can figure that out, right? What's our equation for slope?
Y equals mx plus b.
Yeah. The change in y, which for us is, well, I'll just put change in y first, divided by the change in x, right? And so that's the change in the natural log of the concentration of N2O5 in this case, divided by the change in time. And if all we had was data, we could do this by hand if we really wanted to. They've given us a couple of data points here. And so our slope, remember, is equal to negative k. So negative k is equal to that change in concentration. And we're going to start at the final point and subtract the initial point or an earlier point. And so negative 1.5 minus negative 0.34. And that's divided by the change in time, 2430 seconds minus 400 seconds. And so the negative k negative 1.16 divided by 2030 seconds. We end up with k being 5.71 times 10 to the negative 4 per second. Okay. And that's if we were doing an experimental lab, for example, and we didn't know the rate constant, and all we had was the raw data. We could take that raw data, plot it in Excel. And since Excel gives a trend line, we could just add a trend line, or we could just do it by hand, take the natural log of the initial data point and later data point, and figure out the rate constant that way. So using raw data, okay? Not just requires a little algebra, right? So let's see. One of the things that we use kinetics, this is chemical kinetics for, is half-life. Maybe the most famous half-life example is carbon-14 dating, you know, how old is this fossil, that kind of thing. But a more applicable one, in my opinion, one that's used by a lot more people, is something like the half-life of a drug in your body, right? Pharmacists and doctors want to know how long a particular drug is going to stay around, and so they calculate the half-life. In other words, when does the concentration in your blood go down by a factor of 2? And so the half-life has this symbol, T sub 1/2. And this is the time required for the concentration of a reactant to decrease by half. And so in other words, T, our time in our reaction, is equal to the half-life, T 1/2, when the initial concentration, or sorry, when the current concentration is equal to that initial concentration divided by 2. Right? And so we can think about that a little bit and say that when we take the natural log of all of this business, so if we plug all this back into our rate law equation, so remember natural log of the concentration, well now the concentration is equal to this rearrangement of natural log of the initial concentration over 2 equal to the natural log of the initial concentration minus K, and when we plug in this, the time that we have is T1 half. Okay, so this is using the same exact equation that we used for the last problems, except making this substitution and this substitution, right? Instead of the concentration of A, if we're at exactly the half-life, the concentration of A is exactly half of our initial concentration. And if we're exactly the half-life, the time is equal to the half-life. So rearranging things, we get the natural log. So if we subtract natural logs, that's like dividing what's inside the natural logs. And so the natural log of A0 over A0 over 2 is equal to K, oops, that's not a K, T1 half times K, sorry. So I did 2 algebra tricks there, right? The first, when you subtract natural log, you divide the values. The second thing that I did is when you multiply a natural log by a negative, so I got rid of this negative here. When you multiply a natural log by a negative, you invert it, right? And so that's what I did. I did both of those things to get this equation. Now, A0 divided by A0 divided by 2, all this just goes to the natural log of 2. And then I'm going to get the half-life by itself. I'm going to divide through by K. Now, the natural log of 2, there's no variable there, and so we can go ahead and replace that with a numerical value if we want to. And so for first order reactions, the half-life is equal to 0.693 divided by K. And so for first order, the half-life is 0.693 divided by K. 0.693 is just the natural log of 2. That's what that came from. Since this does not have any variable in it, we can just convert that to a number and get rid of that natural log. Okay. So graphically, what this looks like is that we have, again, it's a first order thing. Let me write that up here. We're going to have different equations for second order. So first order reaction looks like this. If we count up the dots in the first cube, in the first box there, right, we've got 16. And then at this point, we're down to just 8. And so this must be a half-life. Right? T a half. 1 minute. Right? Now we can think about it as, okay, 8 is now our starting point, and we're going down to something else. Well, if we're cutting it in half again, that's 4. and then that's another half-life. Getting into 2, that's another half-life. The key takeaway here is that the half-life does not depend on concentration. Again, T half is equal to 0.693 over K. Concentration doesn't have any role in calculating that half-life. It's just the rate constant. The only thing that we care about when we're looking at the half-life is the rate constant for that particular reaction. That's why the half-life is constant. The first half-life is exactly the same length of time as the second half-life, is exactly the same as the third, the fourth, etc. Okay, so we have ethane that's decomposing into methyl radicals. And this is a first order reaction. We're given our rate constant K. And again, as I told you, every time we have a rate constant, we should be given a temperature. And there it is. So calculate the half-life of the reaction in minutes. Again, that equation T1 half 0.693 over K. This one asks for it in minutes as well, so be careful with your units. What kind of half-life do we get for this ethane decomposition?
21.5 minutes.
21.5 minutes.
Dr.
So
Davis,
yes,
would like anything change if there was a coefficient in front of the reactant or no?
not at all. No. Not at all. Okay. So the reason that we like first order reactions is because their math is super easy, right? Their decay, once we take the natural log, there's a little caveat there, but their decay follows that straight line. The half-life doesn't depend on concentration at all. We just need to know the rate constant. And so first order reactions are super straightforward, and we don't worry too much about them. Second order reactions, things get a little bit trickier, but not terribly so. For a second order reaction, again, we're going to take just sort of a standard A going to something else. We know still that the rate expression doesn't change, right? It's still negative concentration of A over change in time. But now, because I know that it's second order, my rate law changes. And so it's K times concentration of A squared, right? Remember, that's where that second order comes from. It comes from the power on the reactant concentration in our rate law. So just like we did before in first order, I can set these two things together equal to one another. So the change in concentration of A divided by time is equal to K times the concentration of A squared. Our textbook goes through the derivation of going from here to the next step, but I'm just going to go ahead and write it out for you. What we end up with is that 1 over the concentration of A is equal to 1 over the concentration of A naught, the initial concentration. And instead of minus KT, we get a plus KT. And I wrote all over it. I'm sorry. Okay. So again, our goal is to manipulate these relationships so we get a nice linear trend line. First order, we had natural log and a minus. Second order, we have inverse, 1 over and a plus. So here slope is equal to positive K. And the same thing holds true. T1/2 means that the concentration of A is equal to the concentration of A initial divided by 2. If we plug all that into our equation, so 1 over the initial concentration over 2 equals 1 over the initial concentration plus K, and then T in T1/2, the half-life. Okay. We rearrange, and we get that the half-life, T1/2, is equal to 1 over K times that initial concentration. And so we don't need anything other than the initial concentration and the rate constant, but we don't need to know the current concentration. We just need to know the initial concentration. So this one looks a little bit different than the first order, but it's still not terribly difficult. Let's do a quick problem. Iodine atoms combine to form molecular iodine in the gas phase. This is second order kinetics, and the rate constant is huge, right? Remember, iodine is diatomic. Iodine really wants to be I2 rather than I by itself. And so this reaction is going to go very, very quickly. So that's why the rate constant is so very large. Notice too that the units on our rate constant have changed now that we're second order. It's per molar second rather than just per second. So gives an initial concentration of 0.086 molar, and we're going to calculate the concentration after 2 minutes. So 1 over the concentration of I is equal to 1 over 0.086 plus 7 times 10 to the 9 times 2 times 120 seconds. I did a bad thing and I didn't put my units. Molar -1 S times 120 seconds. So 7 billion times 120. I'm going to add that to 1 over 0.086, and I get 1 over the concentration of I is equal to 8.4 times 10 to the 11th. And so the concentration of I is 1.2 times 10 to the -12 molar. super tiny concentration because our rate constant was so large, right? Having a big rate constant like that means that the reaction is going to go super quick. And so this 0.086 molar that we started with reacted away almost instantaneously. And there's just a tiny, 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 tiny bit, 1/1,000,000,000th of a mole left over. So second question, calculate the half-life if the initial concentration is 0.6 and if the initial concentration is 0.42. And so remember the half-life for second order depends only on the initial concentration. And so T1/2 is equal to 1/7.0 times 10⁹ per molar per second times 0.6 molar. And this one is the same except 0.42. These are very small times. Again, remember I told you it reacts almost instantaneously. I got 2.4 times 10⁻10 seconds for the first half-life. And I got just a little bit longer, 3.4 times 10⁻10 seconds for the second half-life. 3.4. Okay. So the higher the rate constant, the faster that reaction takes place, the shorter the half-life. Let me write that relationship up here. An increase in K means a decrease in half-life. Now that's true both for first and second order, right? Because K is in the denominator for both of those things, right? So the larger K is, the smaller the half-life is. All right, that's a good stopping point for today. We will come back on Monday. We'll talk about what are called zero order reactions that don't really depend at all on the concentration of the reactant. And then we will talk about the temperature dependence that I have alluded to a couple of times now. And then we'll be on our way with chapter 13. Right? I hope you have a good weekend. If you have any questions, let me know. Like I said, the quest opens up at 10:25 and it's open until 10 o'clock tonight. So do let me know if you need anything or if you have any questions.
Have a good weekend, Dr.